So now let's get into a discussion of the quantum theory. So we're going to talk about a proposal put forward by this guy Planck. Now he put forward a hypothesis which basically says that if you have a solid that's heated, and as a result of heating it, energy is imparted to the atoms such that they will vibrate, then these atoms that are vibrating can absorb or emit electromagnetic energy only in discrete amounts. All right. So this is something that Planck put forward, and he did some theoretical work, and he came up with this equation here. E is equal to h times nu, right? Which represents the smallest amount of energy that an atom can either lose or gain in, as described up here. All right. Now, E is the energy, as I said before. Now, H is known as Planck's constant, and it has this value, 6.626 times 10 to the minus 34. Let me just say that for our purposes, we'll just round this off to 6.63 times 10 to the minus 34. And please note the units here. The units is joules second. All right, so basically what this indicates is that the energy that is absorbed or emitted by an atom will be proportional to the frequency. So therefore, the higher the frequency, the higher the energy. And that constant of proportionality would be Planck's constant. So basically, according to Planck's quantum hypothesis, the energy that is absorbed or emitted can only be absorbed or emitted as a quantum or whole multiples of quantum. And the energy, of course, is represented by this particular equation. All right, so that's basically his hypothesis. So, of course, in the business of science, people try to test whatever hypothesis that would be put forward. And this is the experiment that was done to do that. So let me describe what's happening here. So what we have here is a photoemissive cathode, which basically means that when exposed to light, it will spontaneously emit electrons, right? And that is placed in close proximity to this rod, which serves as the anode. And it's enclosed in a glass casing right here. And of course, these electrodes are connected to an external circuit. You have an ammeter here, which is basically showing whether or not a current passes through. And then basically when the photoemissive material is exposed to light, as I said before, it produces electrons. And what happens in this case, believe it or not, is that the electrons, what are emitted, will actually travel through space from the cathode to the anode. So basically you have the circuit flowing in this part of the region, in this part of the setup, which allows for the current to be flowing in the external circuit right here, which would be detected by the ammeter, as I said before. So basically, this is what happens. Now, as I said before, the energy of the photon here, well, back up. Let me talk about photons. Photons is a concept that was first put forward by Einstein. And he basically considered electromagnetic radiation to exist not only as a waveform, as we were discussing earlier, but also as small particles known as photons, right? And this setup actually supports that concept, because what was discovered was that only photons with a particular frequency above the threshold limit will cause a current flow. So what that means basically is that if the frequency is below a certain value, it doesn't matter how intense the light is, no current will flow in that particular setup. But once the frequency gets to above or at a certain threshold value, then all of a sudden you'll see the current flowing through the circuit. So what this shows is that the current is not dependent on the intensity of the radiation as reflected by the number of photons, but on the energy of these particles, which is proportional to the frequency. All right. So that's basically, it gives credence to the concept of photons, and it also gives credence to the whole idea of the quantum. All right. Okay, so this leads us now to investigating how all of this is related to the atomic structure of atoms, right? Now, if you recall, we talked about the fact that hydrogen, when subjected to an electrical discharge, it glows and produces radiation. So Niels Bohr, this guy that you see right here, he took into consideration that experiment plus the whole concept of the fact that the energy of an atom will change by discrete units known as quantum, and the fact that electromagnetic radiation can not only exist as a form of wave, but also as a stream of particles known as photons. He took all those things into consideration to come up with his working theory of the hydrogen atom and how the electrons are arranged. So Niels Bohr found out that the electron energy is quantized in atoms, and in particular in the hydrogen atom, and each specified energy value is called an energy level. So the Bohr model of the hydrogen atom is what you see here. Basically, each of these orbits here represents an energy level, but Bohr believed that the electrons actually exist in these orbits, right? The orbits that are closer to the nucleus will have a lower energy, and as you go from closer to further away from the nucleus, the energy of the orbits increases. So he designated these orbits by the letter n. So n equals 1 would be designating the orbit that is closest to the nucleus, and then you have n equal 2, n equal 3, and so on. And he came up with this formula right here. En is equal to minus b divided by n squared, right? That would represent the energy of a particular orbit that the electron would occupy. And b is a constant, which is known as the Rydberg constant. I'm going to say more about this constant later on, because there seems to be, and I say seems to be because it's not actually a conflict, but seems to be a conflict in terms of what this constant is. It's called a Rydberg constant. Let me write that down here. So Rydberg constant. All right, that's what this is. 2.179 times 10 to the minus 18. Okay, so the negative sign here, very important, because it basically indicates that there's a force of attraction that exists between the electrons in the orbits and the positively charged nucleus. And of course, as I said before, basically the energy increases as you go from the lower orbits to the higher orbits, which means basically that when n is equal to infinity, En would be equal to 0, all right? So therefore, that represents a situation where the electron is pulled so far away from the nucleus that the electron is not in any way experiencing any attraction with the nucleus, and therefore its energy relative to the nucleus would be equal to 0. Okay, so how does this explain the line spectra that we observe for the hydrogen atom? So basically, when an electron makes a transition from one orbit to another orbit, basically that's where the energy changes takes place. The energy either increases or decreasing, right? Or decreases. So basically, if you have the final energy level or the final orbit, its energy will be given by this formula right here. And for the initial energy level of the transition, it will be given by this formula right here. So therefore, when you find the difference between those two energy values, you just plug these values here. It's the final minus the initial into this equation, which simplifies to give you this equation right here, all right? So the delta E would be equal to B times 1 over Ni squared divided by 1 over Nf squared, all right? Another way of stating it, and in fact, let me get out of this and pull up a blank page here. So as I said before, let me show you how this is done. Oh, let me do, where is it, pen? Okay, so as I said before, the energy level of a particular orbit would be equal to minus b times 1 over n squared. Now, in some textbooks, in fact, in most textbooks, the b will be represented by RH, which is a Rydberg constant. So I'm going to be using RH instead. So En will be equal to minus RH times 1 over n squared, right? So this is what I'm going to use, right? So if you're doing E initial, right? That would be equal to minus 1 over n squared initial, and E final would be equal to minus 1 over n squared final. So therefore, delta E, I'm just showing you in detail how we derive that equation, would be equal to EF minus EI, and we plug these values here, these expressions here, into this equation, and we're going to get, oh, I forgot to put the RH. So let me put RH here and RH here. So basically this will be equal to minus RH over n final squared. So that's for EF minus RH over n squared initial. And then this would simplify by factoring out minus RH times 1 over n squared final minus 1 over n squared initial. All right? Okay, so basically that is what we use to find delta E. All right? And as I said before, RH is equal to 2.18 times 10 to the minus 19, excuse me, joules. All right? Okay, so that's basically the formula for calculating delta E. Now to calculate the frequency, remember now, delta E, the energy of the transition, would be equal to H times nu. We saw this equation earlier. So to find nu, that would be equal to delta E over H. All right? So basically, to find an expression for the frequency, well, before we get to that, another thing I want to mention here, and I should have mentioned it here. Remember we said that C is equal to lambda times nu, all right? So we can include that in this expression right here. Nu is equal to C over lambda. So basically, lambda, or I should say 1 over lambda, would be equal to delta E divided by H over C, all right? So you'll notice that H over C is basically a collection of constants, because H is a constant, C is a constant. So let me see here. How do we deal with this? So if we plug this here, or for delta E, if we plug this into this equation, we're going to end up with 1 over lambda is equal to minus RH over HC times 1 over n squared F minus 1 over n squared I. Okay, and here we have a collection of constants right here, all right? So let me just put those numbers in. So this will be equal to minus RH, which is 2.18 times 10 to the minus 19 joules over H, which is 6.63 times 10 to the minus 34 joules second, times C, which is 3.00 times 10 to the 8 meters per second. Whoops. Times 1 over n squared F minus 1 over n squared I. Okay, and then let me just work out what that part gives. So 2.18 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34 divided by 3 times 10 to the 8. Okay, so when you round this off to 3 sig figs, you're going to get, let me squeeze it down here, 1 over lambda is equal to 1.10 times 10 to the 6, and the units, when you cancel out the joules and the seconds, would be meters to the minus 1 times 1 over n squared final minus 1 over ni squared. Okay, so basically we have two equations to work with, right? We have this equation here. In fact, let me produce another, use another page since I've completely, okay, so basically we have two equations that I have derived. One equation is delta E is equal to minus RH times 1 over n squared final minus 1 over n squared initial, right? And the RH in this case is, as we said before, 2.18 times 10 to the minus 9 joules, right? But the other equation I derived just now is this equation, 1 over lambda is equal to minus 1.10 times 10 to the 6 times 1 over n squared final minus 1 over n squared initial. Now, the reason I went through all of that is because, and this might sound a bit confusing to you guys, it turns out that in some textbooks, this is known as the Rydberg equation. But in other textbooks, this is also known as the Rydberg equation, all right? And furthermore, even though, as I said before, this is known as Rydberg constant, the 2.18 times 10 to the minus 9 joules, this here is also known as the Rydberg constant as well, right? RH. And the units here is meters to the minus 1, let me add, very important, right? So I thought I should just go through this so that, you know, if you look in different textbooks, you're not confused. Basically, different textbooks and different even internet sources. If you go on the web and you type in Rydberg equation, in some cases, you're going to see this equation here. In other cases, you're going to see this equation here, all right? But what I will say is that both equations are different ways of saying the same thing. Now, this equation I would use if I want to calculate delta E, right? So if you're given the information here, the initial and final orbit values, n, the n values, and the RH, then basically you can find out what delta E is. However, if you want to find out what the wavelength is, I would use this formula right here. 1 over lambda is equal to all of this here. So it all depends on what you are given and what the question is asking for, all right? Okay, another thing, well, before I even say that, let me get out of this here. So let me do keep. Let me go back to the PowerPoint to say something more about how this relates to the line spectra, because basically what happens is that the line spectra that we see for hydrogen can be explained based on the Bohr model, and that is shown in this diagram right here. So basically, when the hydrogen in the tube is subjected to an electrical discharge, energy is acquired by the electrons, and therefore those electrons will be moved from lower orbits to the higher orbits according to the Bohr model. And then what happens is that they fall back to lower orbits and produces the different colors of light, because as it falls from, let's say, n equals 3 to n equals 2, as you see here, the energy changes, and that energy loss is due to the light that is produced, which would be the red light that you would observe in the line spectrum of hydrogen. And that is explained also that is used to explain also the formation of the blue light and the purple light as well. So that's basically how the Bohr model works in terms of explaining the line spectrum of hydrogen. Let me just define some terms right here so that you can further understand what's happening when it comes to the line spectrum. Let's define these different terms, the ground state and the excited state, right? Now, the ground state of an electron is where the electrons are in the lowest possible energy levels, right? So the electron in the hydrogen atom in the n equal 1 orbit would be said to be in a ground state. Any other state are known as excited states, which are of higher energy. So if you have the electron promoted from n equal 1 to any higher state, then basically the higher state is called the excited state. So that means, again, in the case of the hydrogen atom, n equals 2 and upwards, n equals 3 and so on. Now, how are the electrons promoted from lower energy levels or lower orbits to higher orbits? Well, these are the ways that it can happen: by electrical discharge, heat, lasers in the form of photons, and then what happens is that the electrons will eventually drop back to the ground state, and that process is called relaxation, right? So we have excitation when the electron is promoted from the lower energy levels or the lower orbits to the higher orbits, and then you have relaxation when the electrons fall back to their ground state position, all right? So using a Bohr model, we can have an understanding of what happens when we have these electronic transitions. So in this diagram here, let's say you have an electron in the n equal 1 orbit, then it gains enough energy to be promoted from n equal 1 to n equal 5, right? So basically, energy must be absorbed, again, in the form of radiation or electrical discharge, to go from n equal 1 to n equal 5. On the other hand, you can have electrons in higher orbits losing energy, and as a result goes down to lower orbits. So you can have the transition, for example, of an electron in n equal 4, and then it goes down to n equal 2, all right? Or you can have the electron going from n equal 4 to n equal 3, or n equal 3 to n equal 2. So we have, those different possibilities. So when you have the electrons moving downwards from a higher orbit to a lower orbit, energy is released, all right? And energy is released usually in the form of electromagnetic radiation, and that's where you see the different colors of light being formed or produced as a result of those transitions, all right? Now, some quantitative relationships here. The energy gap of the transition is inversely proportional to the photon wavelength, and that should make sense if you think about it. Let me go back to the PowerPoint here, the empty PowerPoint, I should say. So basically, remember we said that delta E is equal to h nu, which is equal to hc over lambda. So if you look at the equation, you'll see that there's an inverse relationship between delta E and the wavelength, right? So basically what that means is that as the wavelength increases, delta E decreases and vice versa. So going back to this, right, as I said before, the length or the energy gap represented by the length is inversely proportional to the photon wavelength. So shorter wavelengths correspond to higher energies with respect to the frequency of the radiation involved, and vice versa. Longer wavelengths correspond to lower energies of the radiation involved in the transition. Okay, I'm going to stop here. The next video will deal with de Broglie's concept equation. Okay, so until next time.